So we're going to start to solve different exponential and logarithmic equations. So we're using more logs. How do we solve for a variable if the variable is the exponent, things of that nature. Properties that we want to keep in mind here, this is that concept of being a one-to-one function. Anytime you have an exponential function where the bases are the same, and this is a strategy that we're going to see down below. If the bases are the same, then we know our exponents are equal. So that gives us this property then where we can set the two exponents equal in order to solve. Same thing is true for any log function. So if you have two log functions where they both have, again, that same base, then what I know I can do is I can set those numbers equal to each other and solve. So with those strategies in mind, let's take a look at number one. And we're going to try and solve for x. And x is in our variable. So the very first thing we want to do is think, let's get as much we can get away from the variable as possible. So in other words, that 20. So first thing I'd want to do is think, let's divide each side through by 20. So that'll leave us with 1/2 raised to the x over 3. And then 5 over 20, when we simplify, that's going to be 1/4. Now, kind of like our concept that we had up above, if I can have my bases to be the same, then I can set my exponents equal. So I want to think, how do we get the bases equal? So I always think try and almost reduce, try and make smaller. And even though these are fractions, they would work kind of the same way as if they were whole numbers, like a whole number of base 2 and a base 4. So I'm going to take this 1/4 and rewrite this so it's 1/2 squared. Thinking if I square a fraction, I square both the numerator and the denominator, that would still produce that 1/4. Over here, I don't have to do anything. That is in that 1/2 style. So I already see that my bases are equal. So since my bases are equal, now I can set my exponents equal. And in order to solve here, if I multiply through each side by 3, that's going to leave me with x equaling 6. So that's that concept of trying to get your bases to be equal. Okay, moving on. If we look at log equations, now there's different ways that we can solve some logarithmic equations. Things that you want to be careful of is to keep track of the domain. Because we want to make sure, sometimes when you solve, just like before, we would get some extraneous roots. We want to make sure that we don't get those here. Or you don't want to forget about some either. Okay, so if we're going to solve this, and keep in mind this is our common log, so this is like that imaginary log base 10. We could do a change of base. We could solve this by introducing a base 10. Up to you how you'd want to do it. I'm going to take it and I'm going to think to myself, this is a common log base 10. I'm going to raise it to that exponent of 2 and set it equal to our number of x squared. Now, here's where you have to be careful, because it looks like I could just say, well, no problem, x has to equal 10. If I do that, keep in mind what you're doing. You're actually losing a solution. 10 squared is really 100. And then if I were to actually solve this, I would want to think, well, introduce a square root. And when you introduce a square root, now you get both the positive solution and the negative solution. So we can actually get two numbers here. Just be very careful when you're looking back here. It looks like you should only say, ooh, x is 10 and I'm done. So make sure that you're going through solving the entire thing. Don't lose a solution. Okay, a little bit more of a complicated problem. Even though it's natural logs, again, it's going to work the same way. First thing that we want to do is think, well, I want to try and simplify the left side as much as possible. And I see an addition. And when I'm simplifying, addition with logs turns into multiplication. So I have the natural log of these two numbers being multiplied. So be careful because I'm going to take both of those. Okay, and on this side, I can think, well, a coefficient that really came from an exponent. So this is really the natural log of x squared. So now I can see my bases are the same. They're both natural logs. So kind of like we said before, if the bases are equal, I can set the numerical values equal. So right now I have left 3x minus 2, x minus 1, and that equals x squared. So we're going to expand this out. We're going to do a little distribution here. And if we expand, we're going to have 3x squared. Outside we get negative 3x. Inside we get a negative 2x, so there's a negative 5x plus 2 equals x squared. So what we want to do is get everything on one side, so I'm going to bring our x squared over. So that gives us 2x squared minus 5x plus 2. And so now we're going to do a little hard trinomial factoring, meaning I need something that's going to multiply to be 2, and it's got to add to be a negative 5. Okay, so if we're going to multiply to be 4, and add to be a negative 5. So if we're going to find something that multiplies to be 4 and adds to be a negative 5, we're looking at the numbers 4 and 1. And I always think sign of my middle term, since it's negative, has to go with my larger factor. And then if I multiply, I think a negative times a negative would get me a positive. So the two numbers I'm looking for are going to be a negative 4 and a negative 1. So hard trinomial factoring. Copy your first term, copy your last term, fill in the blanks with the two values that we just found. And then you're going to factor by grouping. So out of these first two terms, I can pull out a 2x, and I'm going to be left with x minus 2. Out of the second one, I can factor out a negative 1, and again, I'll be left with x minus 2. So keep in mind your hard trinomial factoring, you want to see that repeated factor. So if we were to regroup this now, I have 2x minus 1, and I have x minus 2. And if we solve, we're going to see x is equal to 1/2. Or we're going to have x is equal to 2. Now again, we always want to check, and we want to see what am I able to solve for, what am I able to have as far as the value goes, am I going to get any extraneous solutions? And in fact, this, x equaling 1/2, that's going to get us an extraneous solution. If we go back up to the top, we had natural log of x minus 1, and if we plug that 1/2 in, we get the natural log of a negative number. You can't have a natural log of a negative number, it doesn't exist. So that would be an extraneous solution. So really the only solution to this problem is going to be x equals 2. And then one of our more complicated problems is a great application problem. It is trying to solve perhaps a temperature, time and temperature. So we look at this a lot with cooling. This is Newton's law of cooling. So things that we need to know from this formula is what does it all mean first off, and how am I going to plug this in? So variables, T of M, temperature of the surrounding medium, what we're putting it in to cool. T sub O, that's your initial temperature. Little t is time. Big T, like right here, this is a temperature at a time. So at some specific time. K is a constant, so that we get to solve for. And whenever we're doing these Newton law of cooling problems, I always think you got to solve for it twice. Once to find the constant, once to find what you're looking for, which is typically time. So for number 4, we have here a hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees water to cool. So if I even just stop and think, what did we just find? That's your initial temperature is 96 degrees. The medium, what we're placing it in to cool, is 16. 4 minutes later, the temperature of the egg is 45 degrees Celsius. So that's a temperature at a specific time. So what that's telling me here is my big T of little t, T of t, is 45 degrees when I know my time is 4 minutes. So those two things are connected. Then it says use that law of cooling to determine when the egg will be 20 degrees. So that makes me think, okay, when I solve this, remember we said round 2, when I solve this the second time, I'm looking for my temperature to be 20 degrees, that means I'm solving for the time that's going to match up with it. Okay, so first thing that we're going to do is we're going to plug this into the formula. So we have T of T, so that's 45, is equal to temperature of the medium plus, we need the initial value minus the temperature of the medium times E, that's your exponential function, raised to the negative constant we don't have, the time we have is 4. So we need to go through and we need to solve this. And the thing that we're solving for is that constant. Okay, so we have 45. If we simplify within the parentheses, we get 80. E to the negative 4k. Orders of operations, we want to subtract the 16 first. Don't be fooled and try and combine the 16 and the 80. Okay, subtracting that out, we're going to get 29 equals 80 e to the negative 4k. Kind of like we did with that first problem on our notes, we're trying to get e by itself. So I want to think divide through by 80, get everything away from that exponent. So we have e to the negative 4k. And if we divide this out, we're going to get somewhere around 0.3625. Now, trying to solve for that constant, and it's stuck in an exponent, and I want to get that exponent to come down. Great place to introduce your natural log. Natural log and E are inverse operations. They reduce out. So I have negative 4k on this side, and on this side we have the natural log of 0.3625. So if I divide through by negative 4, now we're going to have that k value, that constant that we're looking for, and that gets us about 0.25368. Okay, using that constant now we're going to go back. We're going to say, okay, I have my constant. What I'm really trying to do is figure out when the egg is going to be 20 degrees. So here's round 2. 20 degrees now goes in for your T of T. Our medium temperature doesn't change. That's still 16. The initial doesn't change. So that's all staying the same. E is still E. Now this time I have my K value, so I have a negative, because that's in the formula. K value is 0.25368. And this time we're solving for T. Okay, so we do the same process. So I'm going to simplify within the parentheses first. So again, that's going to be 80. So don't forget we're going to have there. So we have 80 e to the negative 0.25368t. Subtracting over that 16. So now I have 4 is equal to all of this. Again, trying to get our exponent to be as simple as possible. So we're going to divide through by 80 on each side. And that's going to leave us with about 0.05. And just like we did before, I want to bring that exponent down. So I think if I introduce that inverse operation of E, which is the natural log, do it to both sides. Now we're left with the natural log of 0.05 is equal to negative 0.2536t. And solving for t, now we're dividing through by that negative constant on each side. And so what we find now is our time. And we were looking for the time. Our time is about 11.81 minutes. So almost 12 minutes is when we're going to get to that 20 degrees that we were looking for. We'll practice some more of this in class, and I hope this helped. Have a great day.